Welcome to section 6.5, Applications of Rational Expressions. So here's a question. What work is required to be shown for application problems? Well, if you're recall, we need to have a let statement, an equation, the solving needs to be shown, and then lastly we need a sentence for your final answer. Because it's given in word form, you need to answer in word form as well. And then what are the main kinds of application problems? Well, we have work problems, then we have motion problems. These are the ones where you usually see miles per hour, and this one's usually talking about work. And then after that, we have mixture problems. This is usually when you are mixing items. And then after that, we might have something that would be geometric, which would be talking about shapes. So if it's talking about a square field or a rectangular something. And then we would have one which I would just call formula. This is where they give you a formula, and then they should have asked you or tell you how to use it. So let's take a look at example 1. In physics, the focal length f of a lens is given by the formula 1 over f equals 1 over p plus 1 over q, where p is the distance from the object to the lens and q is the distance from the lens to the image. Solve the formula for p. So this would be considered a formula problem because they already give us the formula, so you don't have to take that time to create the formula. It was already given. These are usually a little more simple. So we have the formula and we're told to solve it for p. Once again, one thing to note, if you're given lowercase in formulas, stick to lowercase. Don't change to capital or vice versa. If you're given one, stick to the one you're given. Alright, so where is p? P is down here in the denominator. So what I'm going to do is I'm going to get rid of all of the fractions. To do that, I'll use my lowest common denominator of f pq. And let's go ahead and multiply that out. Once again, I'm trying to solve for p, and to do that, I'm going to get it out of the denominator first. So when we distribute that in, and the f cancels with that f, we're left with pq equals fq plus fp. Because the p canceled and the q canceled. Alright, let's check and make sure that makes sense. Yep. Alright, so now I'm trying to solve for p. Where is p at the moment? We have it right here and right there. So I'm going to get the ones with p on one side, and then I'll try factor. So we have pq minus fp equals fq. Alright, so let's go ahead and factor out the p, and what's left over? Q minus f equals fq. Okay, still solving. Let me just rewrite this down on the side. Oh, and one thing to note. Since we have the equal signs going along in the middle, we no longer need the equal signs on the outer side. Okay? So make sure you're only using the equal signs in the middle when you're working with an equation. That was something I noticed on the last exam. Alright, so solving for p, let's go ahead and divide by the q minus f. And p equals fq over q minus f. And we solve for p because it only shows up in one place. Right there. Alright, so for part b, this is a little incorrect. This should be find p if q. Okay, so let's go ahead and use our formula with that little correction in place. So we have that q is 20. So we'll replace 20 wherever we see q. And then that f is 10. So let's go ahead and show the substitution for that. That is something I'll be looking for. Make sure you do these substitutions. Especially when you're given a formula. So that's going to be 200 divided by 10. And then we can just go ahead and cancel the zeros. I love division with hundreds. That'll just be 20. So what does 20 mean in our problem? 20 is the distance from the object to the lens. So let's go ahead and write that sentence. the distance from the object to the lens is 20 centimeters, period. Once again, always remember your units, for example, centimeters, and make sure that your sentence is specific to the problem. So I mentioned, for example, the information, distance from the object to the lens. All right, let's take a look at the next problem. In your mathematics class, 3 of every 4 students are girls. If there are 28 students in the class, how many are girls and how many are boys? Now this type of problem is not actually mentioned above. I'll go ahead and add it in. This would be a proportion problem. How do I know it's a proportion? It is comparing similar quantities, would be a way I would put it. For example, we're talking about 3 of every 4 students. It's sort of a ratio, right? So we know that 3 girls are in 4 students. Would be a way I could represent this mathematically. And then what do I know? Well, I'm trying to figure out if there are 28 students, how many are girls and how many are boys? So you know what, let's go ahead and introduce our variable because we're not given an equation, or we're not given a variable. So when you're not given one, you have to create it yourself. And to let your readers know what they stand for, we read a statement. So let x equal number of girls, and let's let y equal number of boys. So we know that there are 3 girls out of every 4 students. I can create another ratio and set these two equal to each other. Well, that must mean that in the 28 students, how many should be girls? Well, we don't know exactly, but we're going to say it's x. X of them are girls. And we've created a ratio with something that we know, 3 out of 4, and our one variable here with the other item that we do know. And note, students and students are on the bottom, girls and girls on the top. So your units should be in the same area. So let's simplify this without the units for now. 3 over 4 equals x over 28. Solving, let's multiply both sides by 28. So that cancels there, and then simplifying. 4 can go into itself once, and 4 can go into 28 7 times. So then we're just left with 7 times 3 equals x. So 21 equals x. What does that mean? That's the number of girls. So we know that there are 21 girls in the class. Well, how many boys are there? So I'm going to go ahead and label my work here. Solving for boys. Well, we know that that's just going to be y is equal to 28, which was the total number of students, minus the number of girls. So that's just going to be y is going to equal 28 minus 21, the number of girls. Which means in that class, there are going to be 7 boys. That's a very interesting mix. So 21 girls in the class and 7 boys in the class. Alright, so let's take a look at the next problem. Jody's car uses 10 gallons of gasoline to travel 210 miles. She currently has 5 gallons of gas in her car. She still needs to drive 640 miles. If the car continues to use gasoline at the same rate, how many more gallons will she need to add? So we're not given a formula, and we're not given a variable, which means we need to decide and create our own. And remember, the variable pretty much always comes from the question. Once again, the variable basically always comes from the question. And what is the question? It's how many more gallons will she need to add, and that is our variable. So let's just be generic. Let x equal number of gallons she will need to add to her tank. Okay, so now what do we know? Well, we know a ratio. We know that in 10 gallons, they use 210 miles, or they travel 210 miles. So that's my ratio. I'm comparing. 10 gallons is 210 miles. So I can solve if I can set this equal to some ratio with my variable in it. Well, let's see. We know that she needs to drive 640 miles. Okay, so I can go ahead and use that. 640 miles. How many gallons of gas does she need for that? We don't actually know. That's what we're trying to figure out, right? We're trying to figure out how many more gallons she needs. Ooh, we have to be careful. To add. She already has 5 gallons in her car. She's not starting on empty. So she already has 5, and we're figuring out how much more we need to add to the tank. Okay, and there we have created our proportion. So let's go ahead and solve. And when I do this, I'm going to go ahead and drop the units for solving. So cross multiplying, I have 10 times 640 equals 210 times 5 plus x. Once again, just cross multiplying. And I can do that if I have a fraction equal to a fraction. Okay, so that's going to be 6,400 equals, let's go ahead and distribute that 210. 210 times 5, that'll be 0, 5, 10. 210x. Now I just realized the numbers are all rather big here. I might want to simplify it. And in fact, I could have simplified on the step before. I'm going to go ahead and divide everything by 10, just to get rid of all those extra zeros. Once again, remember, we need to divide every term by 10. We can't be picky and choosy about dividing. Okay, so what are we doing? Well, we're trying to solve for x, right? So let's go ahead and keep solving for x. Let's minus the 105 from both sides. And what do we get? Okay, so let's just go ahead and do this by hand. Let's see, so borrowing from the 4, we get 3 and then 10. So 10 minus 5 is going to be 5. Oops, wrong pen color. 3 minus 0, 3, and 6 minus 1, 5. Equals 21x. Ooh, we're almost solved. Okay, so dividing everything by 21. Alright, so we have x equals 535 divided by 21. Okay, so if you have access to the calculator, you can type that in. If you're not allowed to use the calculator, let's go ahead and check this with some long division. So 21 into 535. 21 times, let's see, 3 would give me 63. That's too big. 21 times 2 would give me 42. That would work. So 1 or 2 minus 42. That's going to be 1, 1, bring down the 5, 15. Okay. I have a feeling this might be a long decimal. So how many times can 21 go into 115? Let's make a guess. Let's go with 6. Just guessing that because 25 quarters, remember if you think of quarters, you get 4 quarters give you $1. And we're looking for something a little around like $1.15. So I'll go with 6 and that'll be 6, 12. Ooh, too big. So let's go with 5. 21 times 5, what would that be? 5, 10, 105. Okay, let's go ahead and write that down. So 21 times 5 is 105. And we're left with 10. Bring out the decimal, bring down a 0. How many times can 21 go into 100? Well, a little less than 5, right? Because 21 times 5 gave me that 105. Let's do 4. 34, 84. That'll be 4.4 because we had the decimal. Minus 84. And 100 minus 84 is going to be 16. Bring down another 0. And basically, once you hit past 2 decimal places, usually, unless you're told otherwise, just go ahead and round off in this class. That'll be 160, and how many times does 21 go into 160? Well, it's more than 105, so let's go ahead and multiply by 7, maybe. That'll be 7 and 147. We might be able to get closer. So let's do 21 times 8. That'll be 8 and 16. 168. Ooh, too big. So it looks like 21 times 7 is going to be the answer. And then after that, we'll go ahead and leave our answers. That looks like the answer will not round off soon. So we'll go x is approximately 25.47. And this would usually be scratch work on the side. I'm going to go ahead and erase it. So, are we done? No, not quite. We need to answer as a complete sentence. What is the question? How many gallons will she need to add? So she will need to add about 25.5 gallons of gas. Period. All right, let's keep going. So, Keiko's boat travels 12 miles per hour in still water. Find the rate of the current of the river if he can travel 6 miles upstream in the same amount of time that he can go 10 miles downstream. What kind of a problem is this? Well, you'll notice we have some keywords, miles per hour. This is a motion problem. So for me, whenever I see a motion problem, I like to set up the motion word box. Different textbooks do it differently. This is the way I do it. As long as you have a way of organizing the work nicely, it works. And we'll use the formula for motion, which is distance equals rate times time. And we have two different options. He's going upstream and he's going downstream. Now, what are we trying to figure out? We want to find the rate of the current. So that will be what I'm trying to figure out, what I don't know, right? That'll be my variable. Let x equal the rate of the current. Okay, so what else do we know? We know that going upstream, he can travel 6 miles. Okay, so that's my distance. And then going downstream, he can travel 10 miles. Once again, my distance. Let's draw some lines to keep things separated. What else do we know? We know that he travels 12 miles per hour in still water. However, we can't just put the rate as 12. Why not? Because it's being affected by the current of the river. If I'm going upstream, my speed of my boat is going to be slowed down, right? Because I'm trying to struggle against the current of the stream. So the rate of the current is going to be pushing against my 12. So it's going to be 12 minus the rate of the current when I'm going upstream. However, when I'm going downstream, the current will be helping my boat move faster, right? So it's going to be the rate of my boat plus the rate of the current when I go downstream. Kind of sneaky. But just imagining yourself trying to kayak up a stream or something, it'll give you a good visual. And then after that, what do we know? Well, if you recall, the last box we fill out is usually the one we use for the equation. So I need to fill out this last box, which means I need to manipulate the equation distance equals rate times time. And I want to solve for time. To do that, I'll divide by r, and I find out that d divided by r equals time. So now I can fill out my time box using this formula. So it's going to be my distance, which will be 6, divided by my rate, which would be 12 minus x. And I'll do the same for this, distance divided by rate. And there we go. Once again, it's good to know how to manipulate the formulas. All right, so we filled out the last box, but what do we do? Is there anything we haven't read yet? Let's see, Keiko's boat travels 12 miles per hour in still water. Find the rate of the current of the river if he can travel 6 miles upstream in the same amount of time. My variable has to do with the rate of the current, and we're trying to figure out the time. So we know that these two must be equal to each other, because the time he travels upstream and the time he travels downstream is the same. So 6 over 12 minus x must equal 10 over 12 plus x. The time upstream and the time downstream were the same. Alright, so we've created our equation, we have our variables, let's go ahead and solve. Since we have two fractions equal to each other, we can do cross multiplication. And we get 10 times 12 minus x equals 6 times 12 plus x. All right, let's do the distribution property. And we get 120 minus 10x equals 6 times 12. What would that be? 72. 72 plus 6x. All right, let's keep solving. Trying to get the variable x by itself. All right, let's go ahead and get the variable on one side, so we'll just choose to move the 10 to this side. And then to get the numbers on the other side, I'll subtract the 72 from both sides. Remember, we subtract because it's a positive 72. We're trying to cancel them out. That's why we're subtracting. And then the 120 minus 72. Borrow from there. The 10, 2, so that'd be 8. We have to borrow there. 11. So 7, 8, 9, 10, 11. 48. So 48 equals 16x. All right, and we're almost there for solving. Divide both sides by 16. Let's see, how many times does 16 go into 48? 16 times 2 is going to be 32, too small. 16 times 3 is going to be 18. Ooh, 48. Hey, it goes in perfectly. Awesome. So 48 divided by 16 is going to be 3. So 3 equals x. So what will the answer be? What are we trying to find? We're trying to find the rate of the current, right? That's what my variable stands for. So the rate of my current is 3 what? Miles per hour. The rate of the current is 3 miles per hour. So usually the motion problems tend to be a little more difficult because you have to usually be able to manipulate the equation d equals RT. So remember that little trick. All right, and our last problem for this section. A printer can complete a large job in 8 hours using a new machine. Using an older machine requires 24 hours to do the same job. How long would it take to complete the job using both machines? We're talking about things that are working and completing a job, right? So this would be a work problem. And once I've identified the problem, I always just like to set up the chart for it. So this is the chart that I use for work problems. Once again, if you have another method, that's all right. And I'm comparing how many items. So I have printer 1, which I'll do this one, computing new machine. Actually, you know what? I'll just call it new machine instead of printer 1. And then we have the old machine. And lastly, we're trying to figure out how long it would take to complete the job together. So the first thing I'm going to do is I'm going to write down their rate, or how long it takes them. Let me go ahead and write that down. The time. So the total time it takes them, well, the first one, the new machine, it takes 8 hours. The old machine, it takes 24 hours. And together, we don't know. That's how long it would take. So that's my variable, because remember, the question is always going to be your variable. So I'm going to say let x equal how long it would take. It would take both machines to finish the job. Okay, let's go ahead and fill in the total time. Well, we know the new one takes 8 hours. The old one takes 24 hours. And then together they take, well, we don't know exactly, but we're calling it X number of hours. Now, we're going to fill in the last box. And this box will be the one we'll use for writing our equation. Now, it's a little interesting. We're talking about the rate per hour. So in 1 hour, how much of the job would the new machine have finished? Well, if it takes 8 hours to finish the job, then in 1 hour it would have finished an eighth of the job. Okay, so that'll be the rate, an eighth. In the old machine, if it takes 24 hours total, how much would it have finished in 1 hour? Well, a 24th of it. So all you do, which is easy, is you just take the reciprocal, and that's how you find the rate. Okay, so you just take the reciprocal of the total time that you have. Just bloop, bloop, bloop. Okay, and let's go ahead and use this. What do we know about this? Well, we know that the time it takes the old machine, an eighth, plus the time it takes the new machine, a 24th, should end up equaling the total time, or the total rate, they work together. Alright, let's go ahead and solve. So the two new ones together should equal their total rate. So to solve, I'm going to go ahead and get rid of the fractions. And how do I do that? Well, I need a common denominator. Let's see, 8 and 24. What do they share in common? Well, 8 can go into 24. So I know I need a 24, so these two are happy, but I need to remember that x, so I need to include the x. 24x is my common denominator. Alright, let's multiply both sides by 24x. Remember, we distributed in. Let me go ahead and write that out. So 8 times 24x. Oops, sorry, that shouldn't be 8 times 24x. That should be 1 over 8 times 24x. Okay, let me color code that, waiting on my pen. Okay, so we have 1 over 8 times the 24x plus the 24x times the 1 over 24 and the 1 over x times 24x. Ooh, running out of space. Okay, so simplifying, we get 3, 1, x. Once again, the plan is to get rid of all the fractions. So we have 3 plus x equals 24. Oops, forgot the x next to the 3. Okay, so then we have 4x equals 24. Alright, let's go ahead and bring that over here. Dividing both sides by 4, we're nearing our final answer. Okay, so 24 divided by 4 is 6. Awesome. Are we done? Almost. We're close. It's a word problem, so we need to answer in word form. So the answer would be, well, what does X stand for? It stands for how long it would take the machines to finish the job together. So it would take the two machines 6 hours. That's our unit. Remember the units. 6 hours to complete the job together. See, teamwork. Teamwork always works. Okay, so one thing to note, be careful of your units, especially if you're using a problem that's a word problem. The equation, distance equals rate times time, this is talking about in terms of hours. The distance equals rate times time is hours. If you're given minutes, you need to convert to hours to use this formula, so bear that in mind. Alrighty, other than that, that is it for this section. Once again, if you need help with any of these problems, please drop by the office hours. I'll be glad to help.